It's my pleasure to introduce Sylvia Serfaty, talking about microscopic description of Coulomb-type systems.
Thank you very much. I would like to thank warmly the Colloquium organizers for inviting me to speak here, and Professor Evin and for hosting me so kindly. I will describe some systems that occur in several parts of physics and approximation that have in common that they have repulsive interactions, typically Coulomb-type. And so here are various collaborators that I've had over the years on this topic. So let me first present the question, as it's quite simple to phrase. We want to look at systems where you have n points or n particles at locations x1, xn, and energy is associated to these locations. It's a sum of pair interactions with an interaction potential W and some potential energy, some confinement potential, in fact. Okay, so the interaction here is singular, and we treat two cases. The most common is in what I'll describe is the case where W is a logarithmic interaction, so minus log norm x, and then dimension is 1 or 2, so the dimension of the space where the points live. So this you can call a log gas. And we will also be interested in situations where you have inverse powers of the distance, where S is between essentially d minus 2 and d. I will call that the Riesz case. And this, as you can see, includes the Coulomb interactions in all dimensions greater than 2. So in dimension 2 is minus log, and in dimension bigger than 3 is S equals d minus 2. Okay, so the potential V here is something that is sufficiently smooth and grows at infinity, so that this minimization problem, minimizing Hn, has a...
Why is there a factor of n in front of the summation?
Okay, so there is a factor of n, very good question. Precisely because we want this sum and this sum, the two terms, to be of equal weights. And you can see that because in the left-hand side I have a sum over pairs of non-equal points. There is an order n squared on the first term, and so we put an n in front so that here this is also of order n squared. And in any case, in a lot of cases you can achieve this just by rescaling your system in space. So for example, if V is quadratic, it would just be a matter of scaling. But
you can have S equal to 0 even when D is bigger than 2?
Yes. So if D is...
Oh, it's the
okay,
max.
if
the max.
Yeah, so if D is 2...
It's the max, right?
It's the max, yeah. So if D is 3, it's not... Alright, so as you pointed out, these two terms are of competing orders, n squared. And if you don't pay attention, if you just have the first type of term, then there is no minimum, because minimum will be achieved when all the particles are at infinity somehow, because they repel each other. So if you want to stabilize the thing, you need to confine your system somehow by having some potential here that grows at infinity, which will keep the particles together. And we will also see why such things occur in examples. Okay, so this is what you get when you numerically simulate the minimization of the energy in 2D logarithmic case. You see pretty irregular patterns of points, 29 points here. And let me now, I will start by describing the motivations for such problems and what brought us into this before describing results. So first motivation, and there is no particular order in the motivation. First motivation is in fact related to approximation theory and what's called Fekete points. If you are looking at the logarithmic case, which is, as I said, one of the important cases, minimizers or also maximizers of these expressions simply by taking exponential of the energy or exponential minus the energy, you obtain this. So you obtain product of distances times some exponential weights. And things that maximize such expressions are called weighted Fekete sets. And as I said, they are related to approximation theory. How so? Because when you want to numerically interpolate a function, so when you want to numerically integrate, rather, I should say, you might be looking for good interpolation points. So you want to just sample your function at points and sum that as a Riemann sum and say this is a good approximation for your integral. So where should you put the points? Well, it turns out that depending on the way you want to measure your error, the points should be Fekete sets. The optimal points, the ones that minimize the quadrature errors, are Fekete sets. And people look for such things in particular on manifolds such as the spheres. So there's a whole, if you want, there's a whole area of research related to this and to what they call discrepancy theory, quadrature estimates, etc. And so in particular on the sphere, it turns out that the best way to put your interpolation points is to minimize this expression over points of the sphere. Okay. There's also a connection with the seventh problem of Smale, which is to produce optimizers for this minimization problem, or rather to produce almost minimizers with an error log n, within an error log n of the minimum. And this is considered a hard problem. And so in approximation theory, people introduce precisely these Riesz energy minimization problems, where you see you replace the log here by inverse powers of the distance, and they think of log as the limit case when s goes to 0 somehow. And what's interesting is when you let s go to infinity, on the other hand, then what you recover is optimal packing problems. So you're looking for points for which achieve best packing in space. So there's again a whole line of work happening in those directions. So this is another motivation for looking at the Riesz cases that I presented on the previous slide. Okay, so here is the simulations actually that are produced by this community, that community of approximation theory. You see that's for the logarithmic case, points that minimize the logarithmic energy of the torus. And these are the S energies for S equals 1, 0.8, and 2. And so okay, the image maybe is not super clear, but you can see how the points tend to distribute themselves. So there is a critical S above which the distribution of points will be uniform on the torus, and below which it's not uniform, as you can see here. They call that the poppy seed bagel theorem, for obvious reasons. And so you will see that it's not difficult to characterize the optimal density of these points. The fact that it's uniform, or the fact that it's a sort of characteristic function of a subset here. And what we are after in describing the microscopic structure that you see on these pictures. So if you were to zoom and look carefully at the point patterns, what would you see?
What's the confining potential in this?
So in this situation, you don't need a confining potential because you're on a closed manifold, so the points are not going to fly off.
So the confining potential is like the current of the manifold, if you want.
Yes, if you want.
Infinity outside the manifold.
If you want, yes. But so here you just do the minimization on the manifold with no potential. And the points stay on that manifold, obviously. So the second motivation is from physics, particular condensed matter physics. The first model for us was the situation of vortices in the Ginzburg-Landau model of superconductivity. and also vortices in superfluids and Bose-Einstein condensates, which are very related. Another example is the so-called Ota-Kawasaki model of diblock copolymers. But so let me say a few words about superconductivity and vortices in superconductors. So you know, superconductivity is a phenomenon that happens on certain alloys at very low temperature. They lose their resistivity and they expel a magnetic field. They are able to create their own magnetic field to expel a magnetic field. This is what you see in this experiment where a superconductor is levitating above a magnet. This is the famous characterization of superconductors. It's called the Meissner effect. And what is observed is the particular response to an applied magnetic field. So, as I said, at the beginning, a magnetic field is completely expelled by the superconductor because the superconductor is able to generate electric currents without energy dissipation, which create a counter field to the applied field. But then if you raise your applied magnetic field high enough, it will start to penetrate in the sample, and it will penetrate at places that are called vortices. So it's going to penetrate through some particular locations that are that correspond to vortices in the same sense as vortices in fluids, but maybe I don't have time to get in there. And what's interesting is to see the patterns that these vortices form. And here they are. So these are the patterns observed in superconductors in experiments. And you see there are perfect triangular lattices. So these are called Abrikosov lattices. Abrikosov is the physicist who predicted that periodic patterns, he predicted a square lattice initially, of vortices should be observed in superconductors, and then they were observed. So there's a beautiful success of prediction. He actually got the Nobel Prize for this in 2013, together with Ginzburg, the person who is behind the Ginzburg-Landau model. And so this is what you see, these triangular lattices. I talked about the Ota-Kawasaki energy, which is something different. It has a different source in physics. And here is some numerical simulation where you see, again, a situation with points that arrange themselves quite regularly, but not as regularly as lattice. Okay, so again, these are the type of structures that we would like to be able to explain. And let me mention that in the setting of the Ginzburg-Landau model, you want to explain that within this framework of having a certain energy functional that you want to minimize. So I'm not going to go into details, this is just to show you the Ginzburg-Landau energy, which is a little bit complicated, but not so complicated in here. This is in 2 dimensions, there is a gauge field, there is an unknown function, which is like a wave function, a complex wave function. And the vortices, I didn't define them before, they are really the zeros of the wave function, and they come with a winding number because this is a complex value function. Okay? So what we did with Etienne Sandier, and this was a series of works, is we worked directly on this functional, and we showed that in the end, when, in a certain asymptotic limit, the limit where epsilon goes to 0, the vortices are very, very small. Their core size is epsilon. So in the end, they become points, and you can see them as particles which interact with Coulomb interaction, just like in the beginning, just like the energy that I described. So really, all of that boils down to another system of Coulomb particles in dimension 2 with a logarithmic interaction. This was sort of pioneered by Riesz for simplified Ginzburg-Landau functional, but we're in a situation where the number of points was bounded and fixed. And we would be interested, of course, in the situation where the number of points tends to infinity. Okay, third motivation comes from statistical mechanics. And there you want to look at the same energies, but put them in a Boltzmann factor. So you want to look at the situation with temperature, right? So beta is then an inverse temperature, and you form the Gibbs measure, which is exponential minus beta times the energy. So here beta is normalized by beta over 2. And you divide by a certain number, which is called the partition function, which is just the normalization factor which will make this thing a probability density. Okay, so it integrates to 1. So this is the standard setting of statistical physics with this particular energy. And you can observe that something a little particular happens if the interaction is logarithmic, because then the exponential of the logarithm can be simplified, and what comes out is a product of distances to the power beta times some exponential factors. And if you're in an even more particular case, if beta happens to be 2, then this is the square of a van der Waals determinant. And so it turns out that this structure, the determinant structure, makes this type of probabilities a subset of what's called determinant or point processes. So the fact that there is a determinant there creates an algebraic structure which allows you to essentially compute with explicit formulas a lot of things about such laws. So there's again a very large literature which is based on this point of view. Okay.
What do you do when it's the sphere for this measure?
Okay, so when it's the sphere, you can also look at the same thing, and you would let the points live on the sphere. You don't need the exponential factors.
What do you replace dx1 to dxn by?
d theta 1 to d theta n, you take the polar angles.
Okay.
And that's totally considered, it's called the circular ensemble. Okay, so these particular ensembles, when the interaction is logarithmic and dimension is 1 or 2, they are also encounter a lot of interest from the random matrix community because they correspond to random matrix ensembles. So what are the random matrix models that I'm talking about? There are 3 models that are very easy to describe: GUE, GOE, and the Gini ensemble. So you take an n by n matrix, and first you ask that it's Hermitian. You throw the entries at random according to a Gaussian law, and you make them IID. Plus you impose this symmetry of being Hermitian or here being real symmetry. And then you compute the law of the eigenvalues, which you can compute explicitly, basically, with using characteristic polynomials. And you find that the law of the eigenvalues is exactly of this form, okay? With particular interaction log and particular confining potential V quadratic. And particular temperature, I should say. Beta equals 2 for this GUE and beta equals 1 for the GOE. Okay, so these two random matrix ensembles happen to be particular instances of log gases in dimension 1 with some particular values of the temperature. And here dimension is 1 because the matrix has been assumed to be Hermitian or symmetric, and so the eigenvalues are real. So you have a law on the real line, the law of the eigenvalue. Then there is the Gini ensemble, which is the same thing but with complex entries which are not, where the matrices are not assumed to be symmetric. And then the eigenvalues can be anywhere on the complex plane, and so you get a law for points on the complex plane or for points in the plane, which is exactly of the same form again, with particular value beta equals 2 and V quadratic. Okay, so this is one of the reasons why thinking of V quadratic is sort of the model case to have. And what is observed, so it's Wigner and Dyson who first observed that these random matrix models are particular instances of Coulomb systems. And so you observe that eigenvalues matrices, of random matrices, repel each other, like Coulomb particles. The eigenvalues don't like to be too close. Like it's sort of a lower probability to have multiple eigenvalues. And so this is a point of view where, again, there's a large literature, and you can compute a lot of things explicitly by using the fact that there is a matrix model. So you go back to your random matrix model with your entries, and you can compute things. It's sort of algebra, and that allows you to compute a lot of things. Those things are usually restricted to these particular values of temperature, and certainly they are restricted to dimensions 1 or 2. So more general Coulomb systems do not come from cannot be represented as a matrix model. But those that are well studied thanks to this. There's also connections with what's called the two-component plasma, which is the system where you have particles that interact logarithmically, but instead of having only positively charged particles, you have positively and negatively charged particles. So let's say you have n pluses and n minuses, and they interact logarithmically. Then that's called the two-component plasma, and that's of a lot of interest to theoretical physics. So there are these models that are called the XY model, the Sine-Gordon model, that in which you have what's called the Kosterlitz two-less phase transition. So maybe you heard about this recently because the Physics Nobel Prize this year was awarded for the discovery of this transition. And so again, this can be understood. So this can be somehow traced to systems with Coulomb interactions in the plane. Okay. So I hope I convinced you that there's lots of reasons to study such things.
Are these connections provable? Or?
So some of them are sort of mappings that you can make. So you can map one model into another, and that's completely provable. What's not in some passages are not proven. For example, the Kosterlitz two-less phase transition is not completely mathematically proven. But the mappings of Sine-Gordon and XY to a Coulomb gas, so those things are. If you're interested, you should look at a paper by Tom Spencer. He has a long review paper about the topic, which is very interesting. It contains many models that theoretical physicists really work on. So these are very active topics in theoretical physics. Okay, so now let's go back to sort of very down-to-earth approach. We're going to start again from the same energy, and for now we don't include temperature yet. We just look at the energy and try to understand how it expands, how it behaves as n goes to infinity, the number of points. Okay, so the first thing that you can try to do is something that's been known for like 30 years or so. So you assume that the potential grows sufficiently fast at infinity, and you see that this problem is somehow equivalent to this problem. Okay, so what you do, you take the sum of Dirac masses at points, divide by n, so this you can call this the empirical measure, or the density of points. It's a probability measure, and you assume it has a limit in the space of probability measures, in the sense of probability measures also. Then you expect your energy to scale like n squared, and you can show that the minimum divided by n squared converges to the minimum of this E, and uv will be the unique minimizer of this functional E. And what is this functional? It's just a sort of, a continuum version, if you want. You know. So now you integrate against probability densities. You integrate in RD cross RD. And the only difference between this and that is that here I have to pay attention to remove the diagonal, because W is singular at the origin. And here the diagonal is not removed anymore, because it turns out that minimizers of this are measures that are not singular, and then W is an integrable function near the diagonal. And so the only point in the proof of this that's a little bit delicate is in dealing with this diagonal being removed or not removed. You have to be a little bit careful, but it's not very difficult. And so you can prove that the optimal distribution of points, if you look at minimizers of the energy, converge to this mu v, which is called the equilibrium measure associated with the problem. Okay, so it depends, of course, on v, the potential. It also depends on w, the interaction, and it's unique because this thing is strictly convex. And characterizing this equilibrium measure is one of the topics of potential theory. So this was understood since Frostman, and there was even work by Gauss on this problem. Okay, so we have this distribution now, the equilibrium measure uv. So we know what minimizers look like. We know on a macroscopic level what their optimal density is. This mu v can be characterized in terms of v. So I will make assumptions that mu v has a nice support. Okay, so typically mu v is compactly supported. This is what you expect. So let's call sigma the support of mu v. We assume that sigma is compact and has a nice boundary, say C1, even C2, and that mu v has a density with respect to the Lebesgue measure. So it's really a nice distribution. The density itself, we have to assume that it has a little bit of regularity, like C0 beta, order regularity. And if you're in dimension 1, you want it to vanish not too abruptly, something like that. Okay, so it turns out that in the interesting cases that we saw before, the case where v is quadratic, which comes up in random matrix theory, and for the Coulomb case, you can compute exactly that mu v is a characteristic function of a disk, so properly scaled. Okay, so mu v is just uniform distribution in a disk. So this is maybe the model case that you should have in mind. So this corresponds, in the random matrix setting, this was the Gini ensemble in the plate. If you remember, had Coulomb interaction. So this tells you that the eigenvalues should distribute uniformly in a disk. If you're in dimension 1 and you look at the logarithmic interaction, that corresponds to the case of the eigenvalues of these symmetric matrices or Hermitian matrices. Then the distribution mu is just the graph of this function, the square root of 4 minus x squared. And that's called the semicircle law in the context of random matrices. And what you see is that if you look at the histogram of eigenvalues, almost all the eigenvalues lie in this interval. And if you look at the histograms, you simulate, you will see that, well, the number of eigenvalues that are close to this is close to that. So this can be simulated and give very good match. Okay, so these are the kinds of equilibrium measures that we would like to treat, that we can treat. So keep those types of situations in mind. Alright, so now I remind you that we are also interested in the situation with temperature, and here is a simulation. So I plot the 2D log gas for V quadratic. So as I said, we expect the number of the particles to distribute themselves according to the characteristic function of a disk. And you can see that in those pictures, if you believe in it. And you can also see that when beta is much larger, the distribution of particles seems to be more regular. And where beta is smaller, it's more disordered. So this is what you would expect as the effect of temperature. Beta large means temperature is lower, so there is more order. And beta small is higher temperature, there is more disorder. And this is what we would like to describe. But as you see, this only happens at the microscopic level. So at the macroscopic level, we expect always the same distribution. This is stated in this theorem. This theorem is about the case with temperature. And it tells you that if you look at these empirical measures, now not only of minimizers of the energy, but of all possible states, then there is this thing that in probability language is called the Large Deviations Principle, with this rate function. And so if you don't know this probability language, this is the translation in common words. It says that the probability that your empirical measure looks like a certain, or belongs to a certain set A, will decrease exponentially according to this exponential factor. And what's in the parentheses here is the infimum of E over A minus the minimum of E. So you remember E is this continuum energy that I described in the previous slide. It's minimized at the equilibrium measure. And so what this means is that everything that has an E which is above the minimal value has exponentially small probability. So then the factor here is positive. The only way that you don't have a exponentially small probability is if the infimum over A is the minimum. But since the minimum is achieved uniquely at the equilibrium measure, it means anything that's not looking like the equilibrium measure has exponentially small probability. Okay, so in other words, all configurations with temperature, most of the configurations again look like the equilibrium measure. So you expect them to all have the same microscopic behavior. So the differences that we see on the pictures here, they can only be seen at the sort of next order level, and what I claim is that they can also, it's the same to look at the next order and to also look at the microscopic behavior. The differences will be microscopic and not macroscopic. Okay, so the type of questions we want to ask precisely, so in what sense do you approach the equilibrium measure? Is it true at small scales? So from macro scale to micro scale? The smallest scale that you can look at is n to the power -1 over dimension. If you have n particles and you are in a box of size 1, so the typical interparticle distance that you expect is n to the -1 over. So we'd like to go down to these levels, n to -1 over d, maybe plus epsilon. Deviation bounds, so that's precisely the type of things I described before, Central Limit Theorem. And in particular, maybe in more common words, what you want to do is zoom into the system by this scale n to the 1 over d. And when you zoom, you obtain an infinite point configuration, and you want to characterize or describe these point configurations and understand how these pictures depend on temperature and how they depend or not on V. So there's been a lot of activity, as I said, on such things, in particular in the logarithmic case when you're in 1D, because these can be related to matrix models. And people spend time trying to understand how the local statistics do not actually depend on V. So they do not really depend on the specific structure of V and of mu V. And they call that universality. So universality with respect to the external potential. I'm thinking in particular of the works of Bourdieu, Lernoche, and Yao, which I will quote at the end.
You have already said this, but how are the xi chosen?
They are sampled according to this probability law.
Okay.
Here. They're sampled like this. So there are random configurations. And you want to describe how they are most of the time. Right? Except with very small probability, everything is like this. And this is what you obtain in such a statement, right? Except with very small probability, they look like mu. Okay, so I was describing this sort of picture. You have your configurations, which a priori are random, or just generic configurations, don't think yet. You want to be zooming near a point of the support of the equilibrium measure, so called the sigma, the support. You want to be zooming, you multiply everything by n to the 1 over d, it should be big N. And you obtain a configuration of points which are now separated by distances of order 1. But as n goes to infinity, these configurations become infinite. Right? They fill the whole space. And these are the types of configurations that we need to describe. So this is the blow up. So let's say you can multiply the scale also by mu v of x. This way the configurations, they will always have a density 1. So if you zoom by the right factor, the number of points per unit volume scales like exactly 1. Okay, so one of the things we will do is define an interaction energy for these infinite configurations of points. It will be called W. And then the total energy of the configuration of points, which here is generic, arbitrary, will be the integral of W over all the blow-up centers. Okay, so for each blow-up center, you zoom, you see an infinite configuration, you compute its energy, and then you average that over all the blow-up centers. And that gives you the sort of total energy at the limit for this system. So we start by looking at the sum of interactions, pair interactions, and expand it, sort of exploit the fact that it's a quadratic formula. So I need to integrate twice away from the diagonal, so this means the complement of the diagonal. And here I just replace this summation by an integral against Dirac masses, which again I express as n times the equilibrium measure plus the difference. Right, so you just expand near the equilibrium measure. You know that sum of Dirac masses is expected to behave like n times the equilibrium measure. So there are some cross terms in the expansion, and the idea is the cross terms can be completely computed, and they sort of disappear due to the fact that you're expanding near a minimum. So it's like a Taylor expansion. When you expand near a minimum, the first order terms disappear. And then you're left with trying to compute these terms that depend on the fluctuations. You see the fluctuations between the Dirac masses and the equilibrium measure. But so now this you can see as a sort of new electrostatic system in which you have positive point charges and a negative charge which is smooth, which is more or less uniform. The density of the equilibrium measure. So it's in fact a neutral system with pluses and minuses. The pluses are discrete and the minuses are diffuse. And that in physics is called a gelium. Such a system is called a gelium. So you want to define the Coulomb energy of this gelium. And there is a way to do it.
What's that word? Gelium?
Gelium. Yeah, I don't know what it comes from, I have no idea. But like jelly. I really don't know, but they call it like that. Okay, so the way we compute the energy is we take the yeah, exactly. We take the potential generated by this configuration. So you convert by W, and you call that Hn, and you compute. Essentially, you compute the energy via this object. If you take the limit, so I'll show you the way to do it in the Coulomb case. If you take the limit of such Hns, then n tends to infinity, you will get a function h, which is the solution of an equation of this form, minus Laplace h is the sum of Dirac's minus 1. So after you have done the blow-up procedure that I said, you find yourself with an infinite configuration of points, so-called curly C, this infinite configuration. I identify the configuration with the sum of Dirac masses on the points of the configuration. And I have the neutralizing background, minus 1. Okay, and then you want to compute something which is more or less this. the average over larger and larger boxes. So KR refers to cubes of size R, centered at the origin. You want to average integral of grad h squared over larger and larger boxes, and this is your energy, more or less. So this is these quantities were introduced in different papers with different co-authors in increasing level of generality of the potentials W that we could treat. So at first it was just log in 2D, and then we expanded to log in 1D, Coulomb, and then Riesz. Okay, so roughly it gives you a way to compute these double integrals of the neutralized systems. You see where you have the configurations of points minus the uniform measure. And you take the large box limits of that. So it turns out that you can make a correspondence with such things and such things, as was studied by my student Thomas Blay. Okay, so I don't want to go into too much technical detail. Let's just say that there is a way to define an energy for an infinite system of points, seen as a system of points neutralized by a backup. And we call that W. And then I told you that we were going to average W with respect to the blow-up centers. So this is what is described in this long paragraph with more words. So we're given a configuration, and for now it's just a generic configuration. We zoom near a point X. We zoom at this scale, mu n to the 1 over v. And that's how we obtain these configurations that have density 1. And we average near the blow-up center X. And this gives us what's called a point process in the language of probability, maybe, which is just a measure or probability density on infinite point configurations. It's a little bit technical to say, but it's not so complicated. Then we form something that's called the tag point process, which will be a probability on blow-up centers cross configurations. So if you want Px, so P will be Px of integral of Px of C dc. We'll tell you the probability of seeing the configuration C when you zoom near X. If you want to be more concrete, you're going to take a limit as n goes to infinity, and you're going to zoom, say, near this point. And let's say that when you zoom very near this point, half of the time you see a triangular lattice, and half of the time you see a square lattice. So what I mean by half of the time is, I mean for half of your sequences approaching the point, you see that, and for the other half you see this. Then your Px is going to be half of the Dirac mass at the square lattice configuration plus half of the Dirac mass at the triangular lattice configuration. So it's something that weighs, assigns a certain weight to infinite configurations of points. And then you can define the average of W, so the W bar of such a point process with tags as the integral over all configurations of the point process near X integrated over X. Okay, so as I said, it's just averaging all the W's you see when you extract all the possible limits. And the first main result is we have an expansion of the energy, which is essentially valid for all configurations. So you can apply it to minimizers, but not necessarily. And you expand, as you expect, there is a leading order term that was the term that was known before, n squared times the energy E of its minimum uv, the equilibrium measure. If you're in a logarithmic case, there is a term that comes out, which is fixed, it's n over dimension log n. And in all the other cases, including log, there is a next order term, which is this W bar, times n to the 1 plus s over d. If you're in a logarithmic case, think of s as 0. You can just subtract, you can just erase the s. Okay, so what this says is if you look at next order, in the energy expansion, you pick up the energies of these infinite neutralized configurations. so particular corollary is the situation of minimizers. So if you have minimizers of Hn, now what you have to do is you have to look like the equilibrium measure, and after blow up, at the microscopic scale, you also have to minimize W. If you minimize this, you minimize that. So minimizers converge to minimizers of this W. This is what's written here. If you zoom at the proper scale, you see infinite configurations which minimize W. And of course, we obtain a next order expansion of the minimum. If you have minimizers, we also have a bit more information. We can prove that the points have a good separation, like C over the n of 1 over d power of n, so just what we expect. We can quantify how much, and we can show a certain uniform distribution of points and energy, so this was proven in those papers. And at the beginning, I mentioned to you that the Ginzburg-Landau vortices and Ota-Kawasaki and other things were in fact the same, or they boil down to the same. So we have a theorem in these cases. If you take minimizers of the Ginzburg-Landau energy, then again, you will see vortices which, when you zoom appropriately, converge to minimizers of the same W. So it's exactly the same 2D logarithmic interaction. So this W, we call it the renormalized energy. I don't know if I mentioned that. Same result for this Ota-Kawasaki model. Okay, so we take all these minimization questions and we reduce them to a question of minimizing another energy. Have we accomplished very much? I don't know, but transfer one minimization problem to another where the number of points is now infinite. Okay, so now we can try to look at the question of minimizing this W. And unfortunately, the results are scarce. So there's only an answer in dimension 1. So in dimension 1, and no matter what the interaction is, the minimum of W, you will see it's achieved for the lattice C. So for a perfectly regular distribution of points. So of course you can always normalize, so the density of points is 1, as I say. So W in the 1D is minimized by the lattice. In dimension 2, we don't know, but there is a partial result which says that if you look within the class of lattices, so only within the class of lattices, of fundamental set of volume 1, the optimizer is the triangular lattice. So this lattice. So this is the minimum among lattices. And of course you recognize that this is the same as the triangular lattice that's observed in superconductors. And we derive this W from superconductivity, from the energy of superconductivity. So this is all sort of coherent. So this is what is known. The fact that it's a minimizer among lattices, it's actually a result from number theory from the 50s. Look at this. You look at the Epstein zeta function of a lattice, which is formed this way. And it's known that this is minimized by the triangular lattice. This is only known in 2D. You can ask yourself, what's the best lattice in 3 dimensions or in higher dimensions? So just among lattices, again, within the class of lattices. So there is no corresponding result that's known except in particular dimensions 8 and 24. So there are some exotic things here happening. Certain dimensions, some very particular lattices happen to be good. In dimension 3, it's not even proven which lattice it is, so it's expected that it should be the boundary-centered cubic lattice, this one. But it's not. Okay, so coming back to our 2D situation, there is this partial minimization. Question, is this really the optimum among all possible configurations? So this is, say, a conjecture. In dimension 2, the triangular lattice is a global minimum. Why do we believe this? Because we see in experiments in superconductivity that these lattices are selected by nature, and we know that vortices should minimize W. note that the Vecterin and Sondier showed that this conjecture is equivalent to another one. So that's another reinforcement to the conjecture. The conjecture made by Riesz, Hardin, and Saf on the expansion of the minimal logarithmic energy on the sphere. They made this conjecture by analytic continuation, so by completely different means. So this is another sort of reinforcement. Okay, so now I want to describe in the last few minutes what we can say with temperature now. So these were, as I said, for generic configurations, then for minimizers. And now what about configurations with temperature? So we look at this this probability density, this Gibbs measure on configurations. It's convenient to scale it like this when S is not 0, when the interaction is Riesz. And we are going to insert our next order expansion of the energy, as I said, because I presented to you before that we have a next order expansion. So let's insert it. And this should give us some information. The problem is that it's not enough to insert an expansion of the energy. You also have to understand how it plays with the volume, with this sort of Lebesgue measure. So physicists say it in the following terms. They say for each configuration you have to understand how many microscopic configurations give you the same macroscopic observables. Right? And this in physics, as you know, is called an entropy. It's how many ways you can realize your system on a microscopic basis. So this is like understanding the volume terms. Okay. So this is what we do. And we obtain another large deviation principle, but this time at the next order. And it's saying that the probability to observe a point process that looks like P is decaying exponentially, like exponential minus beta n, times a certain function f beta minus its minimum. So again, you will have exponential decay of the probability, except if you happen to be at the minimum of this f beta. Okay, and what is f beta? Well, f beta is something that has two terms. One term is our average W that I described before, the energy. And one term is an entropy. So more particularly, it's a specific relative entropy of the point process with respect to the Poisson point process, and then you average this over sigma, and you multiply by 1 over temperature. So what is this term? This term is measuring how close you are to looking like a Poisson point process. What is a Poisson point process? It's what you obtain when you throw points in space at random, independently of each other. So the fact that the other points are doing what they're doing plays no role for the new points. And so the configurations become uniformly distributed, but without a lot of specific order. So they're fairly disordered, the Poisson point processes. And so you see, you want to minimize this. So now that's what's happening to the generic configurations of the temperature. They look like minimizers of this. And you see now it's a competition depending on beta, the temperature. Okay, so if beta is very large, that means very low temperature, then this term essentially disappears, and what you want to do is minimize the energy. And if you believe in what I said before, then you want to think that this is going to look like lattices, at least in dimension 2, maybe in higher dimension. And when beta is very small, which means very large temperature, this term dominates, and you want to look like the Poisson point process. So it means the points completely decorrelate, and the system becomes sort of disordered, where you're just throwing points at random. So this is what we characterize with that. And there are three regimes, which is what I just described. When beta is very large, you expect something like crystallization. And beta is very small, you converge to a Poisson point process, and this you can prove completely. And when beta is in between, the two effects are there, and it's intermediate. So it turns out that in those random matrix situations, the point processes were also understood from other means. So they were understood based on the matrix models. And it was known and characterized, the limit point processes in 1D, they are called the sine beta point processes. And in 2D, for the Ginzburg ensemble, they are called the Ginzburg point process. And they are characterized differently. They are characterized via their k-point correlation functions. So, I can tell you what is the probability of seeing a point at x if there is a point at y. This is the 2-point correlation function. You can do this with k-point correlation functions. So the corollary of this is that these point processes can be identified as minimizing these functionals. W plus okay, so in 1D, we conclude the crystallization result because we know, as I mentioned before, that minimum of W is achieved by the lattice. So in 1D, it's true that when temperature goes to 0, you crystallize. In 2D, as I said, it's not known. In the 2D log case, Logarith shows that you can make this result any mesoscale. It's not so important. And I mentioned at the beginning of the talk the motivation of the two-component plasma, the one that's related to Costelli's two-less phase transition, XY model, and things like that. So the one when you have pluses and minuses. So we can treat the 2D two-component plasma with these techniques, the same idea, and this is done in work with Logarith. Okay, so this large deviation principle that I presented, it works for all these Riesz cases that I described at the beginning. So all the Coulomb cases, all the Riesz cases, and the logarithmic cases in 1 and 2D. And the last result, which I'll be very short, is only restricted, it's restricted to the 2D logarithmic case. But it's already a very interesting case. The 2D logarithmic case, what we can prove with the same assumptions as before, we can prove that the fluctuations, what's called the fluctuations of the linear statistics, obey a central limit theorem. So what are we doing here? We're taking a test function f, and we're forming the sum of f of xi. So as we know, sum of deltas at xi should behave like n times the equilibrium measure. So we're taking this minus what we expect it should behave like. Right, so this is a way of measuring how far sum of delta xi, how far it is from n times the equilibrium measure. And this thing is telling you that it's converging to a Gaussian distribution with a certain mean, which is completely explicit, and a certain variant. And the fact that the variance is like this and the mean is like that, it means that the fluctuation, this quantity distribution, is converging to what's called the Gaussian free field. But okay. But what's maybe should be observed about this result is that this is different from a usual central limit theorem, because you see, these terms are of order n, right? You have n terms here, you have n terms here. If you were summing n IID random variables, standard central limit theorem would give you square root of n times the Gaussian distribution. Here, there is no square root of n, it's the Gaussian distribution. So it means this is very much smaller than could be expected. The fact that this is of order 1, typically, is striking. It means that the distribution of points is very rigid. It's approaching the equilibrium measure at an incredibly precise rate. And so that's what's called rigidity. And this can even be localized with test functions that can live on very small scales. So the equilibrium distribution is the approximate distribution with very high precision. This is what was proven. Okay, I had a slide to compare with other results in the literature. I will let you glance through it. I want to quote in particular about Schmidt, Bourgain, Nicolas, and Yao, who have a series of work that are very close to ours. with even the same result as the CFT. And we generalize most of the other previously known results are recovered by ours. And it's also comparable to what was known in Wendy. And I mentioned at the beginning, Bourgade, Erdo-Scherbo for Wendy. So you see they prove what's called universality in V of the local statistics. Okay, so to finish, slide with questions. So many questions remain, as I told you. This crystallization business is not really understood because we don't understand the minimizers of W. We would like to understand, maybe a better way would be to understand the rate of decay of two-point correlation functions. The universality in V is still not understood in 2D. And then maybe one day the two-component cases in the crystallis to phase transition. Okay, so there are many interesting questions on this topic. Thank you for your attention.
Questions?
What was this entropy? Can you say anything more about this entropy measure that you have? Is there a formula for it?
Yeah, so it's a little bit unpleasant the way it's computed. So it's something that exists. We didn't introduce it. It's called specific relative entropy. And the problem is that because you have these infinite configurations of points, what you need to do is you need to take box cubes of size R, you restrict the configuration to the cube, and you take the usual entropy of the configuration of the relative to the Poisson point process in the cube. And this, the usual entropy is computed by integral f log f, the usual relative entropy. And then you take the limits as R goes to infinity, and you normalize. So you have to compute these large box limits of. So the problem, what's sort of disappointing, if you want, with such results is that we finish with objects which are hard to compute. And so it's hard to exploit the result to draw some easy corollary, because every time you would have to compute. There's only very few cases in which one is able to compute such things. So, but there is a formula. It's a sort of theoretical object that's not easy to compute.
There's a lot of stuff in complex geometry that's a lot like this.
Yes, I mean.
So they have geometric understanding.
I think it's not. I think it's a common feature among, I'm sure, many areas of math that you are able to extract an object, but it's not always a completely transparent object.
They have reinterpretations, like they eliminate measures, like before you talk about measures, but they look at some things where you don't need a measure to define them.
I see.
It's nice.
Interesting. Yeah, so the same is true with our W. The W that we have is not easy to compute, except when you have periodicity, then you can actually compute it. You can express it with modular forms, actually. So when you have certain periodicity, you have the Green's function of the lattice, and you can just compute everything with modular forms. But what would be more satisfactory is to have expressions that only depend on these two-point correlation functions. So you know the density, the probability of having a point at x, if you have a point at y, how this decays. So we can express W with two-point correlation functions under some conditions, but then the entropy terms we don't really know. We don't know how to compute them or express them with two-point correlation functions. Probably there is no such expression. So this is the type.
Also, you mentioned this 8-dimensional and the 24-dimensional. Does it rely on this recent work about optimal sphere packing, or is it?
So it's. I think it's the other way around, but yeah, the fact that these 8 and 24 are particular is what led people to hope that the optimal packing could be solved in those dimensions. And then they solved it. But it was already known that 8 and 24 have these particular lattices. Yeah, what they achieved is to prove that they're actually optimal for best packing. And maybe a side remark is, you could think that okay, in all dimensions we expect minimizers to be lattices. It's wrong. So it should be true in low dimension that lattices are the best, but it's certainly wrong in high dimensions. In high dimensions, there is a much better way of putting points than on a lattice. So this you can.
Why does that happen?
What's better than a lattice?
Something more disordered somehow, because you see when you make a lattice in high dimensions, you leave a lot of space between your. There's much more space in higher dimension, right? So it's like there's all these dimensions that you're not exploiting for putting points. And so, for example, for best packing, they can prove to you with a few lines that if dimension is large enough, best packing is not a lattice, because you're not using all the holes in between. You're creating too much hole. And so even for interaction energies like the one we look at, they don't expect the lattice to be optimal. So as soon as you pass dimensions 10, 12, things like that.
Except for 8 and 24.
Yeah, except for 8 and 24, and for certain interactions, but yeah. So there are physicists have a good understanding of such things. But certainly it should not be expected that our intuition is very low dimensional, and it shouldn't be the same in high dimension.
Any other questions? Okay, let's thank the speaker.